On the screen, you can see a specific table for the sizes of capillary tubes used with R134a refrigerant. This table has been exclusively designed for situations where the cooling capacity of the compressor is unknown. It is important to highlight that the table uses the maximum electrical power allowed by the compressor, expressed in horsepower, HP, as a reference. For example, for a compressor of 1/5 HP with an evaporator operating at an evaporation temperature of -6.7 degrees Celsius 20 degrees Fahrenheit, the corresponding values are listed in the table. However, it is crucial to clarify that the best way to select a capillary tube is not solely based on the compressor's electrical power or horsepower, but rather on its cooling capacity. The cooling capacity of a compressor refers to the amount of heat a system using that compressor can remove. This capacity is usually measured in kilocalories per hour, BTUs per hour, or watts, and depends on the evaporator temperature required by the system. It is essential to note that watts can cause confusion, since some manufacturers use watts both to measure the electrical power of the compressor motor and its cooling capacity. When selecting capillary dimensions, cooling capacity is considered more precise than the compressor motor's horsepower, because cooling capacity relates to the refrigerant gas flow and not the efficiency of the compressor motor. On the screen, there is another table, this time with capillary sizes for R134a, based on the compressor's cooling capacity. Before using the table, it is important to know the following key recommendations. Capillary tubes depend on both their length and diameter to determine the total restriction they offer. The primary function of the capillary tube is to slow the refrigerant passing to the evaporator, maintaining the low pressure necessary for the compressor suction. The two essential variables for selecting a capillary tube are A. The evaporator temperature. B. The cooling capacity of the compressor. C. The condensation temperature. Difference between electrical power and cooling capacity. A. Electrical power, in HP, relates to the compressor motor and should not be confused with the cooling power or capacity, as the latter relates to the refrigerant gas flow managed by the compressor. B. Although tables based on electrical power in HP exist, it is more advisable to use tables based on cooling capacity in kilocalories per hour, BTUs per hour, or watts. C. For the same electrical power value, different models of compressors may yield different cooling capacities. D. When calibrating the final size of a capillary tube, remember that a percentage change in the capillary diameter can alter the refrigerant flow more significantly than the same percentage change in length. E. Adjusting the capillary length is a better method for calibrating its final restriction. F. However, using excessively long lengths to increase restriction is not only inefficient, but also ineffective in many cases. In such cases, change the diameter instead. G. Conversely, excessively short lengths cause small changes to result in significant variations in flow, leading to operational problems. On the screen, there is also a pressure and temperature table for our R134a refrigerant, created with different measurement units. This refrigerant is characterized by medium working pressures. Examples of common pressures. Low pressure in freezers for a temperature of -20 degrees Celsius. The table shows an absolute pressure of 19.404 psi. To find the gauge pressure, subtract the atmospheric pressure according to your local altitude from the table value. In this case, you get 4.7 psi by subtracting the atmospheric pressure of 14.7 psi at sea level. Low pressure for equipment at -10 degrees Celsius. The table shows an absolute pressure of 29.4 psi. To find the gauge pressure, subtract the atmospheric pressure according to your local altitude from the table value. In this case, you get 14.7 psi by subtracting the atmospheric pressure of 14.7 psi. Low pressure for preservation equipment at a temperature of 5 degrees Celsius. The table shows an absolute pressure of 51.303 psi. Gauge pressure, 36.6 psi. High pressure with R134a. To calculate high pressure, add 15 degrees Celsius to the ambient temperature and look up the value in the table. For example, ambient temperature, 35 degrees Celsius. Add 15 degrees Celsius to the ambient temperature. Adjusted temperature, 50 degrees Celsius. Absolute pressure, 194.04 psi. Gauge pressure, 179.3 psi.